Welcome back to this lecture on rules of inference and proofs in predicate logic. In this second segment, we're going to look at an example, a concrete example of a proof in predicate logic. And that example will be the following argument. Sentence S1 says, all candidates have won a primary. Sentence S2 states, some candidates have little money. And the last sentence in the argument, S3, states, some candidate with little money has won a primary. So this is an argument. It's a sequence of three propositions, where the first two, S1 and S2, are the premises, and S3 is the conclusion. So the question we're asking here is whether this argument is valid. Remember, the first step is to convert the English statement of the argument into logic. So, in other words, we need to exhibit the argument form of the argument. What logical structure does it have? So first we're going to convert S1 to predicate logic. All candidates have won a primary is a standard form we've seen many times before. It says, for every element in the universe, if you're a candidate, then you won a primary. Let's use the predicates C and W for these two propositions. So S1 becomes, for all x, C of x implies W of x. And I'll let you decide what the universe for x would be, for example, the set of all politicians. Now for S2, we have a sentence of the form, some candidates have little money. That means at least one candidate, maybe more, have little money. So S2 is an example of an existentially quantified proposition, namely, there exists x such that x is a candidate, which is a predicate we already introduced before, and x has little money, which is a new predicate needed for this proposition. Finally, for S3, we don't need to introduce any new predicates, but the sentence says some candidate with little money has won a primary. So that is another example of an existentially quantified proposition, namely, there exists x such that x is a candidate, x has little money, and x has won a primary. So now the question is this argument valid? In other words, is S3 a logical consequence of the conjunction of the premises S1 and S2? So to answer this question, since we're in predicate logic, we can't use truth tables. We're going to have to write a formal proof. Now remember that a formal proof is a sequence of propositions, each of which is either a premise or it's the conclusion of an inference rule whose premises appear earlier in the proof. Now remember that every proposition must be numbered, every proposition must be true, and every proposition in the proof must be justified. So the first line in the proof is always a premise. That's the only way to justify anything when you start from scratch. So let's pick premise S2 as our first true proposition in the proof. It says there exists x such that C of x and L of x. Therefore, there must exist a specific element in the universe for which C of x and L of x is true. This is the rule called existential instantiation, which we applied to the proposition number 1. Now remember, in this rule, we are forced to use a name for a specific element of the universe, but because we don't know what that specific element is, we have to use a name that we haven't used before in the proof, and that's why I chose the constant name A. Now, from this conjunction, we can infer that its first operand must be true, in other words, C of A. That's the rule of inference called simplification, applied to proposition number 2. Now remember, this rule was stated for predicate logic, but of course it carries over to, it was stated for propositional logic, but it still carries over to predicate logic because, hey, C of A is a proposition and L of A is a proposition. So we apply simplification and end up with the first proposition, C of A. Okay, so we're not done yet. Remember, we're trying to get to the conclusion, namely S3. So we're pretty far from it. So the next step I'm going to do is introduce or use premise S1, which we haven't used yet. So I justify it, and then I use it to infer something, namely that if this conditional is true for every element X in the universe, then in particular it must be true for the element A that we saw before. And that's how I infer proposition number 5 based on the rule of universal instantiation applied to proposition 4. Now we can recognize a conditional together with its premise, which should ring a bell and tell you that you can use the modus ponens to infer the conclusion of the conditional. And this is obtained by applying the modus ponens, again, a rule of propositional logic that still carries over to predicate logic, and we apply it to proposition 3 and proposition 5 in a proof. Now we're getting there. In particular, we notice we have this conjunction here about A, and we have this proposition here also about A. So the next step in the proof will be to use the rule called conjunction on propositions 2 and 6 to end up with this conjunction. So what that means is we just found an element, namely A, for which those 3 properties C, L, and W are true. Therefore, we are entitled to conclude that there must exist an X, namely A, for which C of X and L of X and W of X holds. How did we make this inference? By using our new inference rule called existential generalization applied to proposition 7. And now we're done because this last proposition is the conclusion of our argument. So in other words, yes, this argument is valid. The way we proved it is we first converted this argument to predicate logic, and then we proved formally that its conclusion S3 is indeed a logical consequence of its premises S1 and S2.